Okay, hi everybody. So you've already seen a little bit of me, but I didn't formally introduce myself. I'm Rachel Nethery. I am a biostatistician by training, working in the biostats department at Harvard School of Public Health. Obviously, with a particular interest in statistical methods for climate and health research. And I am the co-lead of the capacity building function of CAFE with Pat Kinney, who you heard from earlier. And I'm going to be talking a little bit about commonly used study designs and statistical methods for climate and health research, along with my colleague, Dr. Amruta Nori-Sarma, who's going to take over here and there for me as we move through the slides. So for this session on statistical methods and study design, unfortunately, we can't really start from zero and build up from nothing. We kind of, given the very limited time that we have here, in order to get to the climate and health relevant methods, we kind of need to assume some background with basic statistical methods and inference. So for this session, we're going to assume that you have some a priori familiarity with basic statistical inference quantities like p-values, standard errors, confidence intervals, that you know what those are already, and maybe a little bit about where they come from and the concepts underlying them. We're also going to assume that you have some general familiarity with linear regression modeling techniques. In particular, it would be good if you've seen linear models before. In this session, we're going to be relying specifically on Poisson regression models, which are commonly used in climate and health research, but I realize are a little bit more unusual in a lot of other research domains. So it's okay if you haven't specifically seen Poisson regression models before. But I think at times you may be a little lost if you haven't seen any linear models before. So hopefully you know a little bit of linear models and have some basic idea of how to interpret model output from a linear model. And finally, we are going to be using R in RStudio just a little bit throughout this session. So we are going to assume in order to sort of get the full effect of those pieces, we're going to assume that you've seen R before, you know some basic commands and object types, how to import and look at data. And maybe as a bonus, even how to fit regression models. If you're not familiar with R or you're a user of another statistical software, you won't be totally lost in this session. There are just pieces where things might not be totally clear to you. And so if you are new to any of these concepts, we are linking here some free materials that you can use to get the background and then potentially come back and be able to get more out of this session from the video recording. So there are a few links here for sort of general statistical inference, linear models, and R in this open intro stats book that's freely available. And then specifically for Poisson regression, which again is a little bit more of a topic that's more specific to environmental and climate health research, we would recommend this Poisson regression chapter of the Beyond Multiple Linear Regression book, which is also freely available online. So first, let's talk a little bit about commonly used study designs in climate and health research. So ubiquitous feature of climate and health studies, particularly climate and health studies that want to quantify the magnitude of the effect of a climate exposure on a health outcome, is that they almost always rely on observational data. So experiments of the type that are used in like, for instance, clinical trials are usually unethical when we're thinking about effects of climate or environmental exposures on health, because, for instance, we already have some idea that heat or wildfire smoke are bad for your health, and so it wouldn't be ethical to randomize some people to receive those exposures and other people not to receive them in order to study their and quantify their effects. So most climate and health studies are then sort of stuck with just using observational data that's going to rely on natural variability in exposures and outcomes to try to disentangle their associations. So the purpose of the purpose of climate and health studies can either be descriptive or what we'll call associational or causal. So descriptive studies would be looking to describe a climate and/or health process. So purely to describe it rather than to test a particular hypothesis or to assess associations between variables. And so an example of a recent descriptive study in the climate and health space was the one that produced this figure here, which was describing spatial patterns in California in extreme heat and wildfire smoke co-occurrence. And so what you're seeing in these maps, similar to the ones Heather was showing you how to produce earlier, is sort of the frequency of heat and smoke co-occurrence. That's what HSC stands for, across communities in California, with lighter colors indicating higher, more frequent heat and wildfire smoke co-exposure. And so this study and a lot of other studies in the descriptive climate and health study space are often are focused on kind of identifying communities that are very highly or disproportionately exposed to climate exposures. And also potentially communities that, because of other factors, are particularly vulnerable to the health impacts of climate exposures. So moving forward, while descriptive studies are extremely important, we're going to be focused mostly on methods for conducting associational or causal studies. So that means we're going to focus on study designs and methods for studies that seek to assess associations between a climate exposure and a health outcome. And you'll note that I said assess associations between an exposure and an outcome, and not assess the effect of a climate exposure on a health outcome. So why did I say it that way? So usually, in fact, when we're conducting these kind of studies, what we actually do want in our hearts is to be able to ultimately conclude that our exposure that we're investigating does or does not cause a particular health outcome. But there are some complications to making these conclusions in most climate and health studies. And these complications mainly arise from that observational study design that I was mentioning on the previous slide. So observational study designs have this threat that a phenomenon called confounding can bias their results. So what is confounding? Confounding is when your exposure of interest is systematically associated with other factors that also affect health. And so in this setting, where we have confounding, if we just quantify effects by using simple, unadjusted measures of association between the exposure and the health outcome, those effect estimates will be biased because they absorb some of the effects of these other factors that are related to both exposure and outcome. So in these settings where we have confounding, which is typically in observational study designs, we have to take special care to try to disentangle the health effects of our exposure of interest from the effects of these other confounding factors. So an example actually can be drawn from the data that we saw in the previous slide, this heat and smoke co-exposure study. So we know that wildfires tend to co-occur with heat and drought. And so if we're wanting to estimate the effects of, say, wildfire smoke on health, then we have to disentangle those effects of wildfire. Oh, was there a question? Oh, sorry, I thought I heard somebody ask something. So we want to disentangle the effects of wildfire smoke. So we need to disentangle, the effects of wildfire smoke from the effects of the health effects of heat and drought that are often happening concurrently with a wildfire. And usually this sort of disentangling from a statistical perspective happens via regression modeling techniques, although you'll see later that there are some other techniques that can be used to try to do this. But let's say that you're clever and you realize that heat and drought are possible confounding factors in your study of the effects of wildfires on health. And so you use some statistical modeling to adjust for heat and drought exposures to try to disentangle the effects of wildfire smoke. The problem is that with observational study designs, we can never guarantee that there aren't other confounding factors lurking out there that we haven't accounted for that could be biasing our effect estimates. So even if you're thorough and even if you try to find all these confounding factors and adjust for them in observational designs, we can never guarantee that there aren't more out there that we haven't accounted for and that could be biasing things. So any associations that we see in observational studies always come with this kind of caveat that they might not actually represent causal effects due to potential unaccounted for confounding. And so in this session, we'll probably sometimes use the word association and maybe sometimes use the word effect, maybe use them interchangeably, but just note that there's this caveat implicit in the background that we're working in observational studies and there could be additional sources of bias lurking in the background. Also, in associational studies of climate exposures and health outcomes, we could be interested in either short or long-term exposures, so short or long-term climate exposures, and those either short or long-term exposures could have either short or long-term effects on health. And so we need to decide a priori which of these things that we're interested in, because they require studies of short and long-term effects require different sets of study designs and methods. And so for this session, we're going to be mainly focused on methods for studying the effects of short-term exposures on acute, sort of immediate health outcomes. And the reason that we're focused on this is that that's where the majority of previous climate and health research work has been done, is on short-term exposures and short-term health outcomes. And now I'm going to pass it to Amruta to talk to you about excess event studies.
Thank you so much, Rachel, for starting us off. So yeah, I'm going to dive into a little bit of detail on the different types of study designs and methods that we use for short-term associational studies. We're going to be going into a lot more detail in each of these different types of study designs a little bit later in this session. But I just wanted to also highlight that in the chat earlier, Rachel did share the GitHub page where you can access the R Markdown file to follow along with some of the analyses that we'll be conducting over the course of the next few minutes. So first, I want to talk a little bit about excess event studies. These are studies where we can estimate the number of excess events, excess health events, or excess morbidities or mortalities that are caused by a particular discrete climate exposure. Usually this is done across a very large geographic area, and it's done on an event-by-event basis. And I'll talk a little bit more in detail about the relative pros and cons of each of these different types of study designs in a few slides as well. Now, by comparison, if we have multiple events that are occurring over time, we can utilize time series methods. So time series studies are used to estimate increases in health risks that are due to either discrete or continuous recurring climate exposures. And in order to do this, we leverage data that's collected across many regular time intervals. So you might think of daily temperature and daily morbidity or mortality outcomes. You might think of a wildfire season in which multiple wildfires are occurring. And one of the nice features of time series studies is that the effects can be aggregated across time for one location or for multiple locations. So we'll talk about single site time series methods and multiple site time series methods as well. Additionally, one feature of time series studies that we want to highlight is that you can identify the concurrent effects of exposure on outcome, or you can also look at the lagged or delayed effects of exposure. So for example, what is today's temperature impact on today's mortality events? Or what is today's temperature impact on tomorrow's or subsequent days mortality events? Under certain conditions, a time series study can give equivalent results to other types of commonly used quote unquote causal inference methodologies, including things like the case crossover study design, which we're not going to go into in more detail right now, but we certainly can share resources for how to set up a case crossover study design subsequently in our after our session. Next slide, please. So excess event studies are the first study design that I'm going to describe in more detail. The objective of an excess event study is to estimate the number of excess health events that are caused by a climate exposure. This is in excess of what would have been expected under a business as usual scenario. And so the example that we've provided here is from a study that I was a co-author on with collaborators based in India, looking at a period of extreme heat that occurred in 2010 in May. You can see the temperatures are illustrated in the solid lines on the graph, with the red line showing the daily temperatures in May of 2010, and the blue line showing the daily temperatures average for the same period in 2009 and 2011. And what we observed during that heat wave period is that there was an increase in the daily number of mortalities that were occurring during that concurrent with that same heat wave period. So that's represented in the red histogram in 2010 compared with the blue average daily death counts from 2009, 2011, the same period. And leveraging this excess event methodology, what we were able to do is illustrate that approximately 800 mortalities occurred during the 2010 heat wave period that we wouldn't have anticipated occurring in the same period in 2009 or 2011, because in 2009 and 2011, that heat wave had not occurred. So what we were able to use this study for was a significant and discrete climate event, which was the May 2010 heat wave, occurring across a large geographic region, which was the entire city of Ahmedabad in the northwestern state of Gujarat in India. Next slide, please. So what is the approach that we can use for some of these excess event studies? What we want to do is we want to define the exposure period, which can be challenging because, giving the previous example, what is it that constitutes a heat wave? There are a lot of different definitions for what constitutes a heat wave. So we want to identify the exposure of interest, which could be an extreme heat event, it could be a wildfire event, it could be a strong storm. And then we want to try and select a control period that can be used to inform us what the number of events are that would have been expected under a business as usual scenario, kind of setting up a counterfactual of what would the numbers of mortalities or numbers of health outcomes have been on those days had this exposure period of interest not occurred. And then the way that we compute the excess number of events is that we compare during and after the climate exposure in the exposed area as A, with the control period of the same length in the same area in a different time period as B. And then the number of excess events is simply the subtraction of the control period number of events from the case or climate exposure period of events A. And then we can also estimate the rate ratio as the ratio of A to B. Next slide, please. So one of the challenges of excess event studies is the selection of this control period or this counterfactual. So when we're understanding the setup of the excess event study, we estimate that these studies are adjusting for confounding through the selection of the control period that is believed to be relatively similar to the exposure period in all ways except for the fact that that climate exposure had occurred. So in the previous example, we selected the previous year and the following year to estimate what the mortality impact we would have anticipated under business as usual to be, because there might be changes in the temperature in this region occurring from May to June when there's maybe the onset of the monsoon season, which impacts both temperature and humidity, or there may be other characteristics of an earlier month that would create a scenario in which the control period in the same year, but in a previous month, would not be as similar as we would like to the case period or the extreme heat period. And so that's why we chose the same month of May in the year 2009 and 2011 as the comparison for what was happening in 2010. So it's really important to make sure that when you're setting up your excess event study, you're selecting this reference period that would be as similar as possible on all of the different potential confounders in order to make sure that you're identifying the true effect of the exposure of interest. So for example, if studying excess deaths due to a hurricane, you would want to make sure that other meteorological factors like temperature are comparable during the exposure period when the hurricane was happening and your control period. You should also be aware that there are potential time trends that are happening even within a shorter period of time. One of the things that we do see is that the numbers of morbidities and mortalities that occur on weekends versus weekdays have general fluctuations that can be observable in long-term trends. So comparing a Monday or a Tuesday, the numbers of mortalities to what was happening over the weekend before that may not be a good selection of a reference period. So some of the common choices that we can use under this study design are the same time period from another year as what we did in the case of the India heatwave study. We could also look at the average from the same time period in multiple other years. One of the things that we do want to note, though, from this choice is that there may be long-term trends in health outcomes. Say, for example, if the number of people living in a city grew exponentially between one year and a subsequent year, that might lead to additional issues in some of the baseline population at risk between years that would lead to incorrect inferences if you chose periods from different years as reference points for the year of interest in your study. Next slide, please. So I want to talk through a little list of the pros and cons of this excess event study methodology. So I think that there are actually some really great features that you can leverage from this type of study design. So we're relying here on aggregate health data, which helps to alleviate some of the potential concerns around patient confidentiality and protection of patients. It's also relatively quite easy to understand and explain and interpret, and it's also very easy to set up these study designs, as I'll walk you through in a real world example in a couple of minutes. And in this study design, because we're careful in the selection of the referent period for our case days of interest, we are, in theory, adjusting for potential confounding by design, rather than through developing a modeling structure that we believe will help to adjust for potential confounders on our behalf. However, there are some downsides to this type of study design. The first is that it requires an exposure that is discrete, that is temporally very well defined, and that is spatially constant across the study area of interest. One of the other things that I want to note is, given all of the characteristics, including short-term time trends, long-term time trends, potential differences in the exposures that might be of interest other than your main exposure, it may be difficult to find an adequate control period. So this is something that requires a lot of consideration when you're trying to draw inferences on the excess risk of different events associated with these exposures of interest. Next slide, please. So I think we're actually going to move over to Excel. Right.
Can you see it?
Yes.
Okay.
So I want to share with you the example that we've pulled out here. One of the things that we mentioned earlier during Heather's session is that we were going to be leveraging the wildfire-specific PM2.5 data for California. So this is a time series plot of the wildfire-specific PM2.5, and then, the days of the wildfire season that are occurring. And then this is the time series plot of actually the mortality count by day. And this is synthetic mortality data that we've generated for this example in order to facilitate the implementation of these different study designs. So it's entirely synthetic data. None of this is representative of any actual mortalities that have occurred in these counties. But what the features of the mortality data are is that we're able to look at, on a daily basis, what are the numbers of aggregate mortalities that are occurring on a county by county level across the entire state of California. So here we've pulled out a single county, which is Los Angeles County. And in the period in approximately June to mid-July of 2017, there was a particularly extreme wildfire event, which is highlighted in the center panel in gray. And so for our excess event study, we're looking at the comparison of 2017 with the previous year, 2016, in the same time frame, also highlighted in gray in the top panel, and then the same period in 2018, highlighted in the bottom panel in gray. And so, in effect, what we're looking at is were the numbers of mortalities across this time period in 2017, shown in the gray area of the figure, comparable in 2017 compared to the average of the numbers of daily mortalities that were occurring in 2016 and 2018. And if we see excess events during 2017, can we associate that with increases in the air pollution exposure, the fine particulate matter exposure that people experienced as a result of the wildfire event that was occurring simultaneously? So now we'll go back over to the Excel sheet. And so what we've done here is we've pulled out in columns B through G in the Excel spreadsheet. We have one column for exposure, that is the estimate of daily wildfire specific PM 2.5. For 2016 is in column B, 2017 is in column D, and 2018 is in column F. Those are all of our exposure estimates. And then for each day, we've also pulled out the corresponding synthetic mortality data. So in 2016, that's shown in column C, 2017, that's shown in column E, and 2018, that's shown in column G. And so in order to facilitate the comparison between 2017 and the previous year, 2016, and the following year, 2018, we've estimated the average of daily wildfire-specific PM 2.5 for the period in 2016 and 2018, which we're using as our reference period. And that's shown in column J. And then similarly, we've estimated the average number of daily mortalities in the 2016 and 2018 reference period, and that's shown in column K. And in order to handle any potential fluctuations in the short term in the numbers of mortalities that are occurring within these control periods, another estimation method that we can use is a smoothed average of both PM 2.5 and mortality. So we've chosen here to do a 1 week smoothing average. So this represents the average of the previous 7 days of both PM 2.5 and mortality. So that's shown in columns L and column N. And so what we have here is a very simple overview from the 1st of June until about the 20th of June in the bottom of our table of the daily estimate of wildfire-specific PM 2.5 averaged for the control or reference period of 2016 and 2018. And now we can simply do a comparison of those averages with our 2017 wildfire-specific PM 2.5 and mortality data shown in columns D and E. And the way that we've done that is through a very simple graphical visualization shown in sheet 2. And so what you can see here, very similar to the example that I shared earlier, is that in the plot on the left, we're showing the excess risk of mortality and the wildfire-specific PM 2.5 plotted on the same figure. And what we find is that during the time period in 2017, we can see the wildfire event, which is of interest for us, which starts around the 3rd of July and continues towards the middle of July as well. And we see the numbers of daily mortalities in 2017 highlighted in orange. And then the comparison period, the wildfire-specific PM 2.5 exposure is shown in the gray curve. And the same period, the comparison period mortalities are shown in the blue figure, the blue histogram figure. And then in order to estimate the excess attributable mortality, we do the comparison of the average daily mortalities for 2017 compared with the same period in 2016 and 2018, which is shown in rows 16 and 17 here. And we estimate that approximately 4 additional deaths were attributable to that wildfire period that occurred in June of 2017. And the attributable fraction, which is the comparison of the excess mortality to the actual numbers of mortalities that occurred during that period on a daily basis. And what we see is that there's approximately a 1% increase in the attributable fraction. And then, so this represents the comparison with the very straightforward average. It's 2016 mortalities plus 2018 mortalities divided by 2. And I mentioned that we may want to look at a smoothed estimate of the numbers of mortalities. So we can see that in the figure here to the right. This is the 1-week moving average of daily wildfire-specific PM 2.5 and daily mortalities. So what we can see is that in 2017, we have the entire record of daily mortalities because we haven't done any moving averages. But our smoothed average mortalities shown in blue for 2016 and 2018 start a little bit later because we're aggregating the values from the previous week. And so we don't have data prior to June 7th that's incorporated into this estimation. And then we're looking at smoothed averages of daily wildfire-specific PM 2.5 over time, comparing in the yellow 2017 to in the gray, the average 7-day moving average of wildfire-specific PM 2.5 in 2016 and 2018. And then once again, estimating the excess number, which is slightly higher in this estimation because we've conducted this smoothed average. And then also looking at the attributable fraction, which we see is relatively similar, whether you're using the straightforward average or the 7-day moving average. And so this is a very basic setup. It doesn't require any prior coding knowledge. All you have to do is pull the data in the format that you are interested in into Excel, allows for relatively easy side-by-side visualization of different methods for averaging, and also provides us with an overall estimate of the excess numbers of mortalities that are associated with this wildfire-specific PM 2.5 increase. And maybe we'll head back over to the presentation. And I just want to mention before we move forward with the time series methods that we're going to be discussing in more detail, one of the features that you'll notice from the discussion that we've just had around this excess event methodology is that it's very difficult to estimate confidence intervals. And one of the reasons for that is in order to develop the confidence intervals, you need to have multiple events and you need to run these excess event studies many times. And so that is what would facilitate being able to develop some understanding of what our confidence is in these overall estimates. And so very quickly, if we start to look at multiple discrete events using this excess risk methodology, it becomes very intractable, which is why we're going to move over into time series methods. And I'll hand off to Rachel to get us started on that discussion now.
Thanks, Amruta. Hopefully you're seeing my slides in full screen again. Somebody shout out if that's not the case. As Amruta mentioned, while the excess event study design is really powerful, it has several limitations that some of which we're going to address with time series studies. So like with excess event studies, the objective of time series studies in climate and health research is usually to estimate the change in the count or rate of a certain health event due to an exposure to some kind of climate factor. And in time series studies, a few of the limitations of the excess event studies that we're going to be able to address is that we're going to be able to consider either discrete or continuous climate exposures, whereas the excess event study design is really only appropriate for discrete, well-defined large events. And then we're also going to be able to make use of data from recurring exposures to the same type of event to hopefully get more robust estimates of their effects. And so the time series study design uses data ideally on an exposure and an outcome that are collected over some regular time intervals. So an example of this is from a study of ozone exposure and mortality in London, where for each day during this several year period, the authors collected the daily mean ozone levels in London and the daily number of deaths in London. And so in this study, as in many climate and health studies, the time intervals over which these data are collected is days. That's often the case. And you'll see that we may also need measures of some other potential confounding factors measured over these same regular time intervals that we may need to adjust for in our models. And these data can come from either a single area, as you see here for London, or we could have these time series of both deaths and exposures, or health outcomes and exposures collected from multiple areas, and we'll see how to handle both of those situations in the next few slides. And so unlike the excess event study designs, the time series study design is going to rely on regression modeling tools to adjust for confounding, rather than needing to select this, this sort of referent or control period. And it provides some added flexibility and a little bit less user discretion. So let's first start with the very simplest time series study design, which is where we just have data from a single area, a single site, over time. So what would our data look like in the time series study design, in this kind of simple time series study design? Well, first, as I said, we'd want to have for our outcome, our health event counts for the given area measured across these regular time intervals. And so for a given time interval T, we're going to denote the health event counts for that time period by this Y subscript T notation. And I promise we won't get too deep into statistical notation here, but we do need a little bit to understand the methods being used. Similarly, we'd like to have exposure measured for those same time intervals that we've measured the health outcome. And so we're going to denote the exposure measures at a given time period T by X sub T. And a reminder that this exposure measure can be binary, it can be multi-category, or it can be continuous. So X could take any of those forms. And then we're also going to sort of present this in the general setting where we have a set of covariates that hopefully measured again at these same time points. And we'll denote this set of covariates measured at a given time point T by C subscript T. So what should this set of covariates C contain? Ideally, C should contain any variables that we suspect could be confounders of the association between our exposure and outcome of interest. So remember, these are factors that are associated with both the exposure and the outcome. And if we don't account for them, we could get biased estimates of the effect of interest. So in climate and health studies, it's very common for potential confounders to be other meteorological variables aside from the particular climate exposure that you're studying. So we'd often want C to include some other meteorological variables. For instance, we saw in the wildfire and health setting, potential meteorological confounder might be temperature or heat. So we would want to measure heat then at the same time points that we've measured exposure and outcome. And we'd include heat ideally in this set of covariates C. In addition to these measured potential confounders in C, the set of covariates for these time series studies often include other what we call structural temporal variables that allow us to account for sort of confounding due to temporal trends in both climate variables and health more generally. And these can be used either in place of or in addition to the measured meteorological variables, since meteorological variables tend to have very structured temporal trends. Sometimes we can, if we haven't actually measured all the necessary potential meteorological confounders, we can get around using those explicitly by using these structural temporal variables. So what I mean by that is we might include a measure of what year we're at time t, what month it is, what season it is, what day of week it is. And so indicators of year, month, season, day of week, things like that might also be included in C to be adjusted for in our models. So let's now talk a little bit about what the modeling would look like in this time series setting. Again, the simplest setting where we just have a single site and we just want to build a model to look at, let's say for now, we just want to look at the association between outcome on a given day and that the exposure of interest on the same day. We'll extend that shortly, but let's assume for now that we just want to look at the effects of same day exposure. So in a typical time series modeling setting, we'd assume that the counts of the health outcome at each time point are YTs, are Poisson distributed, where the Poisson distribution is just a commonly used distribution for count outcome data. And then we'd specify a Poisson regression model that looks something like what's shown here in this line, where we're modeling the expected outcome on time period, or let's say in general, just use the term day rather than time period, but it could be any time period. We're modeling the expected outcome, the expected health event count on day t as a function of exposure on day t and the set of covariates on day t. And so what you can see is that if you've seen linear regression models before, the specification of a linear regression model, this looks pretty much just like the specification of a linear regression model, except for this log function over here on the left-hand side. So we're applying the log function to the expected value of y over here. So this log function is called a log link function, and it's a sort of canonical component of a Poisson regression model. It distinguishes it from kind of a traditional linear regression model. And if you're more familiar with logistic regression, which many folks are, this log link function is analogous to the logit function that we use in logistic regression. And roughly speaking, the role of this log function applied to the expected value of y is that it tells the model that this count outcome should always be non-negative. So it has to always be non-negative. So otherwise, this looks very similar to what we normally see in linear regression. The expected outcome at time t regressed on exposure and a set of covariates also measured at time t. And so then, of course, the quantity of interest from this model is the coefficient, the coefficient parameter associated with exposure. Here we're calling it beta 1. And we can estimate this model to get an estimate of all of the coefficients, but most of interest would be beta 1. We can get these estimates using standard software. We'll show how to do it in R, but any standard software would do this. And I'll note that if you've taken an intro stats class, you're probably familiar with this very restrictive assumption that's made by the Poisson distribution, which is that the Poisson says that the mean of a Poisson random variable should be equal to its variance. And that's a really restrictive assumption that we're not going to delve into in detail here. But I'll just note that that assumption is rarely satisfied when we're working with real health outcome data. And if we impose it on our model, as we will do if we assume the standard Poisson distribution, that can lead to distortion of our estimates of standard errors and other inferential quantities. So in standard software, you can specify what's known as a quasi-Poisson model, or you can alternatively use the negative binomial distribution to relax this mean equals variance assumption and usually obtain more accurate standard error estimates. And we'll show how to do that in software in our example. You can also extend this model to allow for nonlinear associations between the exposure and the outcome by adding polynomial terms on X by using splines, or by simply binning your exposure into some fixed number of categories. So then once we've done model estimation using these techniques, once we've estimated this coefficient of interest, we need to interpret it. And so usually in the linear model setting, recall that we'd usually interpret our coefficients as, you know, a 1 unit increase in exposure is associated with a whatever unit increase in the outcome on average. But here in the Poisson regression setting, we have this log link function that kind of messes with this standard interpretation. And so it turns out that usually the most interpretable quantity that we can sort of easily extract from this Poisson regression model fit is the rate ratio, which we get by exponentiating our estimate of beta 1. And the rate ratio tells us basically the relative change in health events or health rates of the health event per 1 unit change in exposure, in this case, concurrent exposure only, since that's all we've allowed for so far. And so we get the rate ratio, the RR, by exponentiating our beta estimate. And we get a 95% confidence interval for it simply by exponentiating the usual endpoints of a 95% confidence interval for beta. So we just exponentiate the upper and lower confidence limits for beta to get the confidence interval for the rate ratio. And so I'll note that rate ratio values larger than 1 would indicate that the rate of the health event increases as exposure increases. So it would indicate, assuming your health outcome that you're measuring is bad, it would indicate adverse effects of exposure on the health outcome, and RRs less than 1 would indicate that the rate decreases with exposure, or that exposure is protective, we sometimes say in the epi setting. So sometimes people also convert the RR into an estimate of the percent change in rate of the outcome associated with a 1 unit change in exposure, which we can get just by subtracting 1 from the RR and then multiplying by 100. And so I'm going to go now to demonstrate how we would fit this type of model in our data example. Where, remember, we're trying to look at the association between wildfire attributable PM2.5 concentrations and mortality, quote unquote, although we've already said that it's synthetic mortality data that we're using. And so we'll show how to do this type of time series analysis in R. Recall that our study area is California, and we have data for a 5-year period from every county in California. And we're going to restrict our study period during each of these years to just the wildfire season. So the data that we're going to be using cuts out data from outside the traditional wildfire season. And so our study period is really just going to be combining data from May to October for each of these 5 years. And so our exposure of interest, again, is the real daily county level wildfire PM2.5 concentrations. We showed how you can get those publicly available online. Our outcome is that synthetic daily county level mortality count. And the covariates that we're going to use in this example are just a few of those structural temporal variables that we want to adjust for. So we're going to adjust for month, year, and whether or not a given day is on the weekend, because as Amruta said, there are often strong weekend versus weekday trends in health outcomes. And so we'll first illustrate how to sort of do this time series analysis for a single county. We'll focus on LA County, as Amruta did in her example. And then we'll show, for instance, how you could repeat this type of analysis, the code to repeat this type of analysis for all the counties in the data set. And I believe the link to the code was posted, to the code on GitHub was posted in the chat earlier, but let us know if you need that again. So first thing here, hopefully you're seeing my code. First thing I'm going to do is load some packages that are going to help me to do these analyses. And then I'm going to read in the data where this data set that I'm reading in already has merged the wildfire PM 2.5 concentrations for each day with the mortality counts for each day for each county. So just to give you a sense of the data structure, this first column in the data set is our county identifier. So the values of this variable sort of uniquely identify counties. The second column is our date, telling us what day each observation corresponds to. The X variable here is the wildfire PM 2.5 concentration. Of course, most of the time it's 0 because on most days there isn't wildfire PM overhead. And our outcome is given in this outcome column, which is again the synthetic mortality counts for each county and day. So you can see that our data are structured into what we call long form, where each row corresponds to a given county and day. And so this is usually the simplest way to work with time series data is to put it into this long form. So first thing we're going to do is just add a few of those structural temporal variables into the data set, because note that while our data set has the date in it, we still need to pull out, for instance, like what day of the week this day is. We need to pull out the year. And so there's a nice package in R called Lubridate that really is helpful for pulling out these like structural temporal variables from dates. So you can, for instance, use the month command applied to the date column in your data set to pull out a new variable that tells you which month each one of these observations corresponds to. Similarly for the year function in Lubridate. Note that I said that we were going to focus only on days during wildfire season. So here I'm just subsetting the data to drop all of the days that are outside of the traditional wildfire season of May to October. And again, using Lubridate functions to extract what day of the week each date corresponds to, and then create an indicator of whether each of those days is a weekend day or not, because remember, we're going to adjust for a weekend indicator as a structural temporal variable in our models. So let's take another look at the data now that I've made these, I've taken these basic data processing steps. So now, in addition to the 4 columns we had to start out, we now have a column that tells us what month each observation falls in, what year, what day of week, and then a binary indicator of whether that day is a weekend day or not. So now with our data in this format, we can start by sort of pulling out the data for just LA County, which I said we're going to start by showing how to fit these models for just a single county at a time. And we're going to use the LA County example. So first, just extracting the data for LA County, where I know it's county identifier here, and I've used that to subset the data to just the data for that county. So the data set now is just subsetted to include only days for LA County. And then this simple line here is all you need to actually fit the time series model once you've done that data processing work. Here we're applying the GLM function, generalized linear model function in R, to fit a quasi-Poisson model. Remember, we said that the quasi-Poisson approach relaxes that mean variance assumption. of the standard Poisson distribution, allows us to get more accurate standard errors and inferential quantities. And so, to fit this quasi-Poisson model, the first input that you give to the GLM function is just your formula telling R what your outcome is, and then separating that from the variables on the right-hand side of the model, your predictors, your exposure and covariates, using a tilde. So outcome tilde, the sum of the predictors. So the sum of the variables on the right-hand side of the model. This is a standard sort of formula argument from R that you would use, for instance, even in a standard linear model setting. So it looks analogous to how you would specify the formula for a linear model to fit in R. Then you, at the second argument, you tell it which data set that it should pull these variables from. So that's our subsetted data to LA County. And then the last argument is you tell it what type of model you want, which here we want the quasi-Poisson model. So we say family equals, after the equals, we tell it what model type we want, which here is the quasi-Poisson. So can fit this model. And then to inspect the output, we just print the summary of the model object, and that tells us our coefficient estimates and the associated standard errors and p-values for each of them. So in particular, of course, our interest is in that rate ratio for exposure, for wildfire exposure. And so this little bit of code here just goes in and pulls out the rate ratio, which, remember, is the exponentiated coefficient estimate associated with exposure and its corresponding confidence interval. And so you can see here that when we exponentiate, we get the rate ratio for exposure, which is 1.008. So it's a number greater than 1, which would, as we said, indicate that exposure is has a harmful impact on health. And because the null value of 1 is not included in the 95% confidence interval, we might conclude that this is a significant effect on the health outcome. So Amruta is going to talk us more through how to deal with a multi-county study design shortly in the next few slides. But I just want to note that the idea is pretty simple for dealing with multi-site time series data. Typically, what's done is actually first separate time series models are fit for each site. So you would go through and separately fit these models for each site, in our case, each county in the data, and then combine those estimates from each site or each county using a meta-analysis that Amruta is going to talk about. So here I'm just showing you quickly how you would fit this same model, go through this same process and fit this time series model for all of the counties in the data. So we have data for each county in California. And basically all you're doing with this code is just looping through, and for each one of the counties, subsetting the data to only the data from that county, fitting the model on the time series data for that county, and then just exporting the output. And so you can do this to fit models for all the counties. I actually, in the code that you can check out on GitHub, I list a couple of different coding options to get those effect estimates for all the counties. So there are a number of different approaches in the code that you can use to sort of loop through all of the counties. And then here I'm just saving the output for all of the counties and exporting it to an external file, so that, for instance, if you wanted to visualize the the effect estimates using another software like Flourish that Heather showed us earlier. You could then export the results and visualize them in another software if you wanted. For simplicity here, I'm just going to do a quick visualization in R so that you can get a sense of what the estimates look like for each county. Oops. So here you're seeing, I think, for each county, the rate ratio and 95% confidence interval, where the vertical line here is at 1. And so you can see that for most counties, their rate ratios are greater than 1, and their confidence intervals don't include 1. So we would usually say that that for most of the counties, there's a significant effect of wildfire, a significant adverse effect of wildfire PM concentrations on mortality. Of course, this is synthetic data, so these aren't real associations. But we do notice that there are some counties for which we don't see any effect, although I believe even the rate ratio estimates that are less than 1, they're not statistically significant because their confidence intervals do overlap 1, they overlap the null. So again, Amruta is going to show us shortly how we can take this huge amount of output from all of the different counties and condense it into one sort of overall estimate of the effect of wildfire PM 2.5 on mortality. Before we get there, I just want to quickly tell you about a couple of extensions that you might use of this model.
Sorry, Rachel, I was actually going to ask, do you mind if we flip the order so that I can share the multi-county analysis? Just in the interest of time, I want to make sure that we're able to share the multiple counties. Great.
Right. Amruta has to jump off a little bit early. So we will just jump straight to how to do the combining of the time series estimates from multiple sites. Let me get this back into slideshow.
Wonderful. Thank you so much, Rachel. So as Rachel has shown you in her example, commonly what we have is values for exposures and outcomes and time series evidence from multiple locations. And what we're looking for is a way to, with statistical accuracy, combine across these different locations, understanding that there may be some features of the data that aren't exactly matching across these different locations. So for example, we might have some counties that have wider confidence intervals because there's fewer wildfire days, or we may have some counties that have wider confidence intervals because the population size is relatively smaller compared to locations where we have a much larger population. So we would like to estimate, in our case, a average rate ratio across these different sites. So as Rachel was saying, the usual approach is to fit a separate time series model to each of the single sites that are included, and then use a meta-analysis in order to estimate the overall effect and standard error. And this is similar to a meta-analysis that you might see across multiple clinical trials, where you're trying to combine the effect estimates that are generated for different individual clinical trials into a single overall understanding of the efficacy of a drug, for example. Alternatively, in our example, you could just use all of the data to build a single regression model for the entire state of California, as an example, using all of the sites and including a site-specific indicator as a covariate within your model. But this is going to give you a lot less flexibility as compared with our meta-analysis approaches that we have available. Next slide, please. So here we have an example from a study across different cities in Canada looking at the relationship between different air pollutants and acute angina and myocardial infarction within these different communities. And what we've shown is that simple random effects meta-analysis pools the estimates across these different sites, taking a weighted average of the estimates, which have been weighted by their statistical precision, measured by either the variance or the standard error. In R, you can implement this really easily using a package called MixMeta. There have been a couple of different versions of this package or different implementations of meta-analysis that have been really useful for time series epidemiology, but MixMeta is the one that's recommended currently. And so I think we'll move back over into the R code. Oh, sorry, no, we're going to talk a little bit about the different methods for generating these estimates across multiple sites. So there are different types of models. There's fixed effects models and random effects models. And this is something that hopefully some of you have some understanding of these concepts from previous statistical courses. But one of the things that I just want to mention about these different modeling types is that fixed effects models don't assume heterogeneity across studies. So the estimates are conditional on the set of studies. So in our case, the county-specific estimates that are collected during the meta-analysis. By comparison, random effects meta-analysis allows some degree of heterogeneity among studies, assuming that county-specific outcomes are randomly sampled from a usually hypothetical population of a lot of different counties. So in a unified modeling framework, we can assess the meta-analysis as a linear mixed effects model. So this is something that we're going to talk about in a little bit more detail in terms of the ways that we could meta-analyze for fixed effects versus random effects models. There are a couple of different ways, next slide please, that are recommended within the mixed meta package. So for fixed effects models, those are usually fitted through a generalized least squares model, assuming that the covariance structure is completely known. By comparison, for random effects estimators, those include maximum likelihood estimation or restricted maximum likelihood estimation. These are likelihood-based random effects estimators representing the most common comprehensive implementation of the linear mixed effects modeling framework. So this is where we're going to be focused in our analysis using maximum likelihood estimation in our case. By comparison, you have some semi-parametric methods, including the method of moments and the variance components methods, but these are only available for models with a very basic random effect structure. So, we don't have the assumption that we completely know our covariance structure in our model, and we also don't have a basic random effect structure, so we'll go with this intermediate of the maximum likelihood estimation method. So I think we can switch over now back into the R code. And this is actually relatively very simple. So in the estimation of the rate ratios that Rachel conducted previously, looking across all of the different counties, which we showed in the figure, we were actually able to pull out not only the rate ratio estimate and the standard error estimates, we also pulled out the variance of those estimates. And this is a component of the model that's available from the generalized linear model. And we've pulled it out into our data set that contains the rate ratio estimates and the standard error estimates as well. So leveraging that variance, because as we mentioned, we're weighting each county based on the accuracy of the estimate and the data that's going in for each of the counties using the variance information, we're able to just use the mix meta function, pulling in the rate ratio estimates and the variance of those estimates, and using that ML method that we've talked about for random effects. And what this provides us with is the estimate of across all of the different counties and across all of the different individual quasi-Poisson models that we've built, what is the overall estimate of the impact of wildfire-specific PM2.5 on the health outcome, in our case, the synthetic mortality data. And we can use the print function to just show that across all of the different counties, we do see an increase in the rate ratio of mortalities associated with increasing exposure to wildfire-specific PM2.5. One of the things that you might have noticed in the figure is that there's one specific county, and we'll pop open the figure so that we can take a look. It's very handy to be able to investigate all of the different effect estimates that we've seen across these different counties. We see one county towards the bottom of the figure that seems like it might be very influential in the overall estimate of the relationship between wildfire-specific exposures and the health outcome of interest. And it seems to be showing a protective effect. But one of the things that we notice is that the confidence interval is quite wide for this one county. And we don't know, there may be features of that county that are leading to this very wide confidence interval. Perhaps it's a very small county that doesn't have a lot of sample size in order to inform the model. So one of the things we might be concerned about is this effect estimate that seems to be quite protective having an impact on the overall effect estimate that we're obtaining from our meta-analysis? So in order to understand that, we reran the meta-analysis, just excluding the data from this particular county, so that we can try and remove its influence and see what happens to our effect estimate. And what we find when we've done that is that we don't see that much of a difference between the new exposure response that we see, approximately 1.005, removing that county that might have been influential. And then maybe, Rachel, if you can scroll up a little bit in the results, we might be able to see, sorry, if you don't mind scrolling up in your console, so that we can do the comparison with the previous. So we see that this was including that particular county. So we don't, because we've used this meta-analysis method, we've provided an estimate of the overall association between the wildfire-specific PM2.5 and the mortality outcome that's relatively stable, even as we bring in additional data that may or may not have a significant sample size, or that we might be concerned in a straightforward averaging might overly influence our estimate of the association. And so I think those are some of the important features of being able to run the meta-analysis using this weighting that's based on the variance of these estimates. And in this figure, which is a new version of the previous figure, we've just included the meta-analysis as the very first line, followed by all of the different county-specific estimates, so that you can see where the overall meta-analysis has brought us in terms of our understanding of the exposure response, compared with all of the different counties that we have in the data set, and building the individual models and estimating the exposure response for each of those individual counties. And it's not going to be as extreme as the most extreme counties, and it's also not going to be as potentially protective of an effect as we see in some of those counties with the wider confidence intervals. So maybe we can shift back over to the PowerPoint.
Sure.
Wonderful. So sorry, go ahead.
Were there more things you wanted to say, or should I go back and loop back to the nonlinearity piece?
I think if you want to loop back to the nonlinearity, that would be great. Sure.
Thanks, Amruta.
Mm-hmm.
So let's see. Okay, so this what you've seen so far is how to do a simple time series model for a single site, and then how to do the multi-site analysis where you do separate models, you fit separate models for each site, in our case, each county, and then meta-analyze them if you want to get an overall effect that lets you, have both, understand both a sort of overall effect across sites and the site-specific heterogeneity. There are other extensions of the simple time series model that come in really handy in climate and health settings. So one of them, thinking back, remember our model. So far, we've just been assuming a linear association between the exposure and the outcome. But we know that in climate and health, many continuous exposures are non-linearly related to health outcomes. So what do we mean by non-linearly related? We mean that a 1 unit change in exposure is not associated with the same change in the outcome for all sort of starting points of exposure. So for instance, going from an exposure of 5 to 6 of wildfire smoke particulate matter might have a different effect on health than going from an exposure of 39 to 40. And so that would indicate that there's a nonlinear relationship between the exposure and the outcome. And a recent study of the association between wildfire smoke PM2.5 and emergency department visits showed that the relationship between wildfire smoke and ED visits is highly nonlinear. So this study that was recently published used a time series approach, and they included a fourth degree polynomial term on the wildfire smoke concentration variable in their model. So again, kind of going back to our model, instead of just having our exposure variable linearly related, they had polynomial terms, fourth degree polynomial terms on exposure in their model. And they could alternatively have sort of characterized nonlinear associations between the exposure and the outcome using splines, or they could have broken the exposure, binned it into some kind of ordered categories. So this type of time series model can accommodate any of those ways of characterizing nonlinearity. Here, they chose to use polynomial terms on the exposure, and that allowed them to see this really, really nonlinear relationship between wildfire smoke concentrations and emergency department visits. In particular, they see that emergency department visits increase with increasing smoke at low levels, but then decrease at higher levels. So over here, an increase in exposure is associated with an increase in ED visits. But once you get out here to higher levels of smoke, an increase in exposure is associated with a decrease in ED visits. So why would this happen? They did some more digging in data in this study and found that this decrease that we see at higher levels is due to behavioral changes that people make during dense smoke episodes. So when people can actually see the wildfire smoke outside, they change their behavior in ways that is actually overall protective of health. For instance, if you see that it's very smoky outside and you don't go outside and you don't get in your car and drive somewhere, you're less likely to, for instance, get in a car accident or something like that. And so that leads to, at high levels, when people make those behavioral changes, an overall decrease in emergency department visits. So the time series model can allow us to see these nonlinear trends for continuous variables. Time series studies also allow us to look at lagged effect of exposures. What do we mean by lagged effects? So many exposures have delayed effects on health. So they may have an effect both on the day that you're exposed and a few days after. And we might want to understand not only how those concurrent exposures affect health, but also how your exposures over the past few days affect health. And so time series studies can allow us to formally model both same day and prior day effects, or what we often call lagged effects. So how would we do this? How would we extend our model to allow for these lagged effects? So let's suppose that we want to estimate the effects of exposure on the same day. So the same day as we're looking at the health outcome, as well as the effects of exposure on each of the previous capital L days on the health outcome today. And L here, the number of lag days that you choose to look at, would be selected by the user, ideally based on some substantive knowledge or substantive information about how long we think the effects of this exposure might be delayed. So in this case, we would just modify our Poisson regression model from several slides back very slightly to accommodate the exposures on each of the previous capital L days. So this looks like the Poisson regression model that we saw before. We're modeling the we're modeling the expected outcome on day T as a function of exposure on day T, same day exposure, and the covariates. The only new piece is this piece here, which sums over all of the lag days, 1 to L. the exposure on each of those days. So this is just the sum of the exposures, the concentration levels on each of the previous L days prior to day T. And then, of course, they have their associated, each of the days of exposure have their associated regression coefficients. And these regression coefficients, the betas here associated with the lagged exposures are often referred to as lagged effects of the exposure. And what you often see in time series studies is a plot like the one shown up here, where you exponentiate your same day effect estimate, your beta 1 estimate, and the estimate of these betas associated with the lagged exposures to get the relative risks, to get the rate ratios corresponding to each one of the same day and lagged day exposures. Okay, so skipping back through the time series stuff. A few last notes about time series modeling are related to sort of more rigorous adjustment for potential temporal trends in your data. So in our real data or quasi-real data example, remember that we adjusted for month of year and year in our model. But what if we think that just sort of independently adjusting for a month of year and year might not be enough to adjust for the temporal trends in other meteorology beyond wildfire smoke, and potentially other temporal trends in health outcomes, and therefore eliminate the confounding effects. So an example of this is that even though we're adjusting for a month in our model, within month meteorological trends might still confound the effects of wildfire smoke. So for instance, even within the month of May, we know that there are probably trends in temperature, right? As we go further through May in the US, the temperature is getting hotter. And also later in May, we're probably more likely to have wildfires. And so even within the month of May, even once we've adjusted for May, we still might have meteorological trends that are further confounding, still confounding the effects that we're seeing from this model. There can also be changes in the size of the baseline population at risk. I think Amruta alluded to this earlier. So the size of the population that's captured by your time series, this can also change dramatically over time in a way that can sometimes confound your effects of interest. And so let's suppose that we want to do sort of, again, more robust and rigorous adjustment for these possible additional temporal trends that might exist in our data. And to do that, we want to adjust our models for study week. So we would include in our model indicators of study week to better adjust for these possible temporal confounders. And let's, for the purposes of the next few slides, let's just refer to each study week as a stratum. So we need to adjust for indicators of strata to further adjust for temporal trends. So we could just throw indicators of strata into our regression model, indicators of study week into our regression model. But doing this would be pretty computationally costly because it requires us to estimate coefficients for each of many strata indicators. So in the case where we're adjusting for a study week indicator, there might be 50, 100 or more of those in our model. So depending on how many weeks of data we include. So it could be very computationally costly to fit this model adjusted for strata. So an alternative option that turns out to give the same estimates of the quantities of interest, but avoids this computational burden is the conditional Poisson or quasi-Poisson regression model. So this conditional Poisson or quasi-Poisson mitigates the computational demands imposed by adjusting for all of these strata indicators by using a statistical trick that we're not going to go into detail about here because we don't have time and it's pretty statistically involved. But the nice thing is that we can use this conditional Poisson or quasi-Poisson model to still estimate the effective exposure adjusted for strata, but without actually needing to estimate the coefficients associated with strata. So it averts that computational demand. And it turns out that it gives estimates and inference for our exposure variable of interest that are identical to what we would have gotten if we just fit the usual Poisson or quasi-Poisson model, formally adjusted for strata and estimating the coefficients for each stratum. And another thing that's appealing in many cases about this conditional Poisson regression model is that it can be shown to be equivalent under certain conditions to another commonly used study design that we haven't had time to talk about here today, called the case crossover study design that's used a lot in short-term climate and health effect studies. And this conditional quasi-Poisson regression model can be easily fit in R using the GNM package and GNM function within that package. And I see that we're a little low on time. I was going to show the example of this in the real data, but I think I'll skip that due to lack of time. But you can see how to implement this conditional quasi-Poisson model if you go to the code that we linked in GitHub for our data example. So just to wrap up on the time series studies, so we saw that compared to the excess event studies that Amruta talked about earlier, some of the reasons that we might want to use time series studies instead are that we can take this multi-site approach that allows us to both understand heterogeneity in the effects of climate exposures on health across multiple locations, and also still get this overall effect that we can report that's pooled across all the locations. So we can understand heterogeneity while still getting overall effect estimates. We also saw that the time series study design allows for continuous exposures, and we didn't show this in our example, but we noted that it can accommodate nonlinear and lagged effects of exposures. It also uses regression modeling to adjust for confounding, in contrast to the excess event design, which requires the user to sort of select some control periods, and it involves some discretion, whereas the use of regression modeling is a little bit more standardized. And as we saw, it provides sort of formal options for doing statistical inference, whereas as Amruta noted, that's a bit tougher in the excess event design. The downsides compared to the excess event design are that it's a little bit less methodologically transparent. Poisson regression models are a little bit more complicated than just taking differences. And it also, if we want to understand the heterogeneity across space, it requires spatially stratified data, and that can particularly spatially stratified health data can be really difficult to get your hands on just because of privacy restrictions. So I see that there are questions in the chat, but I'm thinking it might make sense to finish out giving you a preview of the anticipated future CAFE educational offerings that you can be on the lookout for in the coming months. And then we can do questions at the end, but let me know if folks have objections to that structure. So one thing that we want to cover in future CAFE educational trainings is methods and study designs for studies of chronic effects of climate exposures. So as I said at the beginning, chronic effect studies require a totally different set of methods and designs than these short-term studies that we've been talking about. In particular, they often rely on cohort study designs, which require a whole different slew of analytic methods than the ones we discussed here. They're also considered to be a little bit more challenging and subject to stronger potential confounding effects, because in these chronic effect studies, we typically rely more on variability and exposure and outcome across individuals or across space, and less on variability across time. And that can lend itself to stronger confounding because individuals tend to be more systematically different from one another than does the same set of individuals tracked across time. And so those systematic differences lead to sort of stronger potential for confounding. These types of studies are complicated because over a long period of time that you need to follow people up to see chronic effects of an exposure, a lot of things change independent of exposure. And so it can be quite hard to disentangle the effects of exposure from other factors that are changing over time. So as you can imagine, then these types of studies are much less common in the literature, and most of what's been done, to my knowledge, has focused on the chronic health effects of a single large event. Like, for instance, quite a few studies like this have been conducted for chronic effects of Hurricane Katrina exposure. There's also a recent nice example of this chronic effect studies in the multi-event setting, looking at the effects of drought exposure on mortality. We also noted in our early survey of the community of practice that a lot of community of practice members are interested in learning more causal inference methods specifically. So just do want to note first that many of the methods covered here can be considered causal methods under certain assumptions about the health effect and confounding structures. So I don't want to suggest that you couldn't do causal inference with the designs and methods that we've discussed here today. It just requires being a little bit more formal about your assumptions. And there's also a whole body of causal inference specific literature that's focused on trying to adjust for confounding and extract causal inferences from observational designs. So in the future, we hope to sort of more explicitly bring in the language and concepts and techniques from this quote unquote causal inference literature into our educational offerings. And so with the remaining time, we'd love to get your all's feedback on what gaps that you've seen exist in free online climate and health education or training resources, because we are trying to create a roadmap for the types of education and training resources that we want to develop with CAFE over the next few years. And so it would be really helpful to hear from you guys about the gaps that you've noticed in, again, what's available free and online, so accessible to all, so that we can consider that when we're sort of forming our agenda for creation of these resources. Other announcements from the capacity building function, which Pat Kenny and I are co-leading, is that we're now accepting pilot grant applications. The pilot grant program of CAFE is run through the capacity building function, and so we have the RFA out now for the pilot grants, and the due date for those to submit your application for those is March 15th. And if you have specific questions about pilot grants, you can actually right now, 3 to 4 p.m., join the roundtable that's going on for the pilot grant applications that is being manned by John Levy and Pam Templer, who are leading the pilot grant program. So encourage you to jump over to that roundtable if you're thinking about submitting a pilot. Also, in the coming months, in addition to developing more education and training resources that we hope to make available free and online, we're also trying to build out a climate and health research mentorship network. And so we hope to have more details on that to come on our website and in communications from CAFE. And that is all I have. Pat, did you want to say anything else before we sort of discuss any questions?
No, I don't think so. There's some good questions in the various chats. I don't have them all here because I was away for a minute and came back.
Gotcha.
Joshua has been asking about some missing input data. He's trying to run the R script. I don't know if that's something, but you could at least look at what he said, and then if you have a quick answer, otherwise we could.
Yeah, so I think the issue is that the data need to be merged with the climate data. So I wasn't able to repost the climate data on the Dataverse. And so you'll have to go to the wildfire data source, which is another website that I believe we linked to, download that data and then merge it with the outcome data that you're able to access on the Dataverse to get the sort of merged data set that I was using in the example. Yeah, it's a good point.
Okay.
You see, there are a lot of questions. I'm not quite sure where to start. I don't think we'll be able to get through all of these in the time remaining. So I'm going to start with the question about selecting. Somebody says, is selecting certain months the continuity of the time series is broken and it might be difficult to reflect the different spacing. So if you were formally including like a day of study variable in your models, and you were including it sort of as a if you were sort of using a continuous measure of time in your models, I think that would be true, that you would have to watch out for just taking out huge chunks of time. In this example, we were never actually using a continuous measure of time. So that's a great point, that it gets a little hairier if you're sort of using a continuous time measure and you're cutting out chunks of data or chunks of time, for instance, due to like seasonal exposures. So that's a great point. There's a question of what if the rate ratio, I always want to say relative risk, what if the rate ratio of exposure is 1.001 with a confidence interval just below 1, the lower confidence bound just below 1. Yeah, I mean, I would say that there's been a move in the epidemiologic community away from just purely using these sort of various measures of statistical significance to gauge strength of evidence. So I would say if you have a large data set and you're pretty and you think your results are robust, it's probably still safe to say there's evidence of an association, even if technically the lower confidence limit is below the null value. I think increasingly that's sort of an accepted practice in the environmental epi literature, at least, to sort of acknowledge effect estimates that appear to be strong, even if they're technically not statistically significant. I'm sure there are other opinions on that.
There's one I see that Zach just highlighted, is down towards the very bottom of the list, that about the fact that many exposure measures are at the group level, whereas Some, I mean, if you have individual data, some confounders may be at the individual level. It says, what are the design/statistical methods to address this when you have, I guess, data from different levels of organization? That's a very common thing in environmental.
Yeah, I would say that the approach that I've seen most commonly used, maybe in some of the more impactful studies, is to sort of analyze your data at the individual level and just assign, if all you have is a group level exposure or a group level measure for some variables, just assign those measures to everybody in the group, and still analyze the data at the at the individual level. That's typically preferred, because if you have individual level data and you have some information on individuals that could help you further adjust for confounding, it's typically preferred to keep the data at that level, I think. Also, you often, when you aggregate everything, as we've done in this study, you do often get criticisms of ecologic bias and things like that, which we didn't have time to go into here today. So if you do have individual level data, my recommendation would probably be to analyze it at the individual level, and assign your sort of aggregate exposures as appropriate to all the individuals within a given group. I don't know if Pat has other thoughts.
No, I agree with that. Maybe I
would say also, just to formally acknowledge this is an ongoing area of research of like how to combine aggregate and individual level data sources. And so we actually have a PhD student in our group working on this question. So it's an active area of research, and there are sort of more modern methods out there to more formally handle this, and account for the sort of statistical uncertainty that comes from having some aggregate variables in your model. And so there are more formal ways of dealing with it, but not that I can easily explain here in a few minutes.
Yeah. I came from a background in air pollution epidemiology, and exposure assessment has always been kind of ecological in those studies. In other words, group level, even city level, quite coarse. I think one move in the air pollution field, one development is towards more highly resolved spatial estimates of air pollution. But still, and in spite of the fact that low-cost sensors are increasingly available, they still haven't really cracked into like large-scale epidemiology studies in a way that like it's not yet changing our exposure assessment down to the individual level, getting it down to the individual level, unfortunately. I think with temperature, measuring temperature is a little bit cheaper than measuring air pollution. So I think individual level temperature measures may be something we could start to move towards in some way. But anyway, it's still going to be a problem for some time, but it's a good research problem for young investigators to try to deal with. I had posed a question, Rachel, which I'll dig up here. It's something that's been nagging me for a long time, but I've never had a chance to really ask a statistician the question. So I'll just read it. So given your comment about within-month confounding potential, do you worry about case crossover models that use month stratified controls? I've been concerned that within-month control would be biased for days near the beginning and the end of the month, for which the monthly mean isn't a good estimate. When you have a strongly trending thing like temperature in the springtime, or mortality, in the spring and the fall. Like, I'm worried about sort of the opposing trends of those things. Have you ever thought about that?
Yeah, we're thinking about that right now, where we actually have some real data examples where it really matters if you like how you pick your set of controls, if you pick them sort of within month, if you force them to be within the same month as the case day, or if you allow them to go sort of bidirectionally on both ends and go outside the month, you get really, really, really different, like going in totally opposite directions answers. And I feel like we've made a little bit of progress in thinking about why that's happening, but I don't want to speak sort of decisively on it, because I think it's still kind of an open area, and we're not 100% certain that we've cracked it. We seem to be finding that if you're using the bidirectional design and not constraining your controls to be within the same month as the cases, usually the bias tends to, like, you're getting some bias, as you say, from the within month, because usually you're picking, even if you don't restrict your controls to be within month, usually you're roughly picking them in similar months around the same time of the case. And so we found that typically, if you have that scenario, then of course, let's say you're working in a temperature setting, I guess, I'm not being articulate here, because it's a really hard question. But we found that in summary, the bias on both ends kind of cancels each other out from these within month trends, is basically the long and short of it. So you get bias in one direction from like the left end and one direction from the right end. And then we're finding that it often like cancels each other out. So I'm sure that would depend on exactly how you defined your study period, though.
That's been my intuition, because the case crossover results always compare pretty well with the time series method. So like, I figured it can't be too biased, and maybe it's offsetting bias. So maybe that's the answer, but look forward to hearing more as your work continues in that question. Are there any other, Zach, have you got any other questions that we ought to pose to Rachel?
I think that the only other two questions that we have are about any epi studies that would be accessible and good to point people towards, or a good environmental epi textbook relevant to climate change. And I'll also just highlight that the Whova chat will be active after the session, if it would be useful to share links offline after the session.
Also, so you had some references on some of your slides, including at the end, and so to share those somehow. Yeah,
I think that would be the best option. For the stuff that we covered today, there are a few really good papers that I cite, like more educational papers in the set of references on sort of general approaches to time series studies and to meta-analysis of multi-site time series. So would encourage you to, once we get a chance to post these on the Whova site, these slides, to take a look at the references there. Pat, you might know better than me about like environmental epi textbooks.
Well, there have been a few climate and health books that that propose to be textbooks. I haven't yet found one that I think is really like up to date enough, because there's like a lag with textbooks. I think and the field is changing rapidly, so I tend to fall back towards the emerging literature as the kind of source for, especially in my class where I'm teaching this kind of stuff.
Yeah,
so I'm still on the lookout for a textbook, but maybe there could be like an online, like readily updated version of a textbook at some point that could serve that purpose.
And I will say, just shameless plug, we are, as part of the CAFE capacity building function, developing a list of existing education and training resources that are freely available online. Oh, I see Elaine's telling us to wrap up. So keep an eye out for that on the CAFE website.
Thanks.
Thank you, everybody.
Everybody else, this was a great session.
Yeah, thanks.